All right, so yesterday we went over mirrors and how light bounces off of them. So today we're going to do lenses, and this is, of course, now lenses, of course, light doesn't bounce off of them, it goes through them. But if we have curved lenses, then they do different things, right? Because it refracts through the lens to produce a new image. For example, a image that has been magnified and has been enlarged, or an image that has been reduced, okay? So before we move on, the optical center of the lens is called, the center of the lens is called the optical center. So here's a bunch of different types of lenses that you have. We're mostly going to just be focusing on bioconvex and bioconcave. So from now we'll just call them convex and concave. But then there's a bunch of different lenses here, right? So something like this negative meniscus is something that you would see in your glasses, right? If you wear glasses, that's the kind of lens that's there to help enlarge things for you. So we're going to have that principal axis again. We're again looking how the light rays are going to move through these lenses. So of course it's drawn through that optical circle or center, but perpendicular to the lens surface. Okay, and then now we're going to have focal points on both sides because there's curves on both sides. So first we have the principal focal point, and that is of course where the rays parallel to the principal axis will refract, so converge through the principal focal point. Or if we're talking about a diverging lens, it's where they'll appear to refract from. Okay? And then, of course, since the light can pass through the lens, then the focal point is on both sides of the lens. So that focal length has not changed. There's the distance of the focal length from the optical center. Okay, but here you can have multiple focal lengths. So that depends on the index of refraction of the lens material. So if you have a lower N, you have a longer F, and it does still depend on the radius of curvature. So of course, longer radius, longer F, but it's no longer just as simple as it's halfway the distance between the center of curvature and the lens as it was with mirrors. Okay, so we're going to go over our converging lens and our diverging lenses, just like we had converging mirrors and diverging mirrors. So here's what a converging lens looks like. It's that convex lens. It's kind of like this pot belly shape. All right, so since it's a converging lens, it means it has a real focal point, meaning that they don't look like they're coming from a focal point. All the light rays actually go through this focal point right here on the other side of the lens. Okay, so that's what that means. Since it has a real focal point, it means that all these light rays are actually intersecting and going through that, okay? And then we have a diverging lens. So that is where we have our concave lens that kind of caved in shape. And this one is going to spread the light rays out. So how do we spread the light rays out? It still has a focal point over here, but what would happen if we bend it towards a focal point? Oh, that would just look like this guy over here again, which doesn't really make a lot of sense. So of course, these ones look like they're coming from the focal point on the same side of the lens, and then they go out like that. Okay, so really, really important that you note that, which focal point we're using. So this one is going to have a virtual focal point, okay, because again, it looks as if they're coming from that focal point instead of converging onto the focal point. Okay, so again, convex lens is a converging lens, a concave lens is a diverging lens. All right, so for our ray diagrams, we're going to draw a lens. We're going to have the principal axis going through that optical center, and then we have to label both focal points, but that's probably already going to be given to you. So then, just like yesterday, we're going to place a vertical arrow to show what the object is or where the object is on the principal axis. That'll indicate, its position, size, orientation. And then we're going to draw rays again, and they're going to be very, very similar, just a teensy bit different. Okay, so of course we have our ray that's parallel to the principal axis, and then it's going to refract through the principal focal point, or it's going to appear to diverge from the principal focal point. So again, that's whether we're working with a converging lens or diverging lens, it's going to be a little bit different, okay? And then we're going to have the ray passing through O, and it doesn't bend due to refraction, okay? So light rays that go right through the optical center don't bend. They're just going to go straight through. And then we're going to have the rays that pass through the focal point or appear to pass through the focal point on the other side, and is going to refract parallel to the principal axis. So they are very similar to what we were drawing yesterday, okay? So let's go. First, we're going to do if we had an object beyond 2F. So here's 2F right there. So I'm going to go behind 2F. Right about there. Okay, so my first thing that I am going to draw is the ray that's parallel to the principal axis, and then it's going to refract through the principal focal point. So here we are working with a converging lens. So this one's actually going to go through the focal point on this other side right here. Okay, so just a little note there. Okay, and then I'm going to stop right there at the middle of the lens, okay? But we are going to go through this focal point on the other side. So when we have a converging lens, our principal focal point is on the other side because we know it's going to, all the parallel ones are going to converge through that point. So therefore, that's the way that the light will be reflected in that one. Okay, what do we have next? The next one we had was the ray passing through O, and it does not bend due to refraction. Okay, so here, where's O? That's right at the middle of the lens right there. Okay, and so it's going to go from the top of our object and it's going to go right through O. It's going to do something like that. And then finally, what do we have? We have a ray passing through or appearing to pass through the focal point. So here it will actually pass through the focal point with this one on the same side. And then it'll refract parallel to the principal axis. Okay, so this one's going to refract through this focal point here. All right, so it's going to do something like this. And then again, stop at the middle of the lens there. And then this is going to refract parallel. Okay, so it's going to go along there. And here we go. So where they all converge or meet up, that is where the image will be. So that's what's going to happen to the image. So let's figure out kind of what's going on with this image. It's about right there. Okay, so what are the characteristics of the image? Well, it's showing up on the other side of the lens, and that means that it's real. It also is the product of converging light rays. So again, that is also real, but this is inverted. And also it's smaller. All right, so if with a converging lens, if you are beyond the second focal point, this will actually make something smaller. Let's see what else we can do with lenses. So say the object is right at the second focal point. Okay. I'm going to say it's right there. So again, we have our three rays. So the first one is the one that's parallel and then refracts through the focal point on the other side. So to something like that. And then we have the one that goes right through the center, which again is just right smack dab in the middle there along the principal axis. Okay, there's our guy through the optical center, and then of course the other one is going through the focal point on the same side and then refracting parallel. Don't worry if you don't get them perfect. Sometimes they are a little bit off. But don't worry about it too much. So this is a little over here, but what's actually supposed to be happening is a perfect intersection at 2F. So what's happening is this is the same size, but it's just inverted, right? So it's real, inverted, but it is the same size. Okay, so that's when you have something at 2F. Now what about in between 2F and F? Let's try that. So say I had my object right there. So what's going to happen to this guy? Again, same thing over and over. You're just drawing the same 3 rays. Okay, look at that. Look what's happening. So they're all converging at that point there. So what does our new image look like? Well, it's kind of difficult to tell, but it actually is larger. Now, of course, it comes from a bunch of converging light rays, so it is a real image. It is inverted, and it is larger. Okay, so this is actually how we can zoom in on things, right? This is how, for example, a microscope works. And that's always why when you move it one way, it goes the other. It's because it's actually an inverted image. So there you go. Okay, now if I put the object at F, what is going to happen? So again, let's draw the rays that we know. So the first one going parallel and then through the focal point on the other side. The one going through the optical center. Any guesses what's going to happen? Can we draw the third ray? We can't, because we can't go through the focal point on this side. And also look at those lines. What's happening again? They're parallel lines, and therefore this is not going to create an image. There are no image here if you are at the focal point. So since these refracted rays are parallel, we get no image. Okay, let's keep going. So object between F and the lens. So it's going to be right here. I'm going to draw it close up, and I'm actually going to draw this one a little bit smaller, which you'll understand why in a minute. Okay, so this one's going to be a little bit trickier. Okay, so the first one though is still the same. Draw it parallel and then goes through the focal point on the other side. Okay, second one is still the same, going through the optical center. Uh-oh, what's happening? Kind of look like diverging rays. And then, of course, this one is the one that's kind of difficult now because it can't go through the focal point. So this is the one where it looks as if it's kind of coming from the focal point, or at least we still line up this with the focal point on the same side. Okay, and we do that. And of course it goes parallel. So what's happening here? We have a diverging image. Okay, so this is that situation again where we need to dot back to figure out where the image is going to be. Okay, so I'm going to do that with all these. Going to try and do my best without using a ruler, but we will see. You never know. Okay, and this one's going to be annoying because you got to dot back from there. Okay, Not the best, but you guys get what's going on. All right, there we go. So this is going to be our virtual image because, of course, the light rays diverge here. All right, so this is going to be a virtual image. It is upright, and it's not the same size, it's bigger. Right? So this is also another way to zoom in on something. All right, so that is all the different ways you can have light rays converge on a convex lens, okay? So as you can see, this is one where it has all the different types of scenarios. And just like with the mirrors, the only time it was different was when the object was in between the focal point and the lens, okay? So let's go on to concave concave lenses. And again, thankfully, there's only one situation here with a concave lens. Doesn't actually matter where it goes, because again, this is a diverging lens. So we're going to be drawing our rays a little bit differently. Okay. So let's say I had an object right there. I'm going to see what goes on. How do I draw these rays? So with our convex lens, we would usually, our first one, we would draw to make it go through the focal point and then go parallel. Here, for a diverging lens, it's going to appear to diverge from the principal focal point. What the heck does that mean? It means it's going towards the focal point on the other side. I know. Okay, but just stay with me. So this one, instead of going through this focal point here on the left side, it's going to look like it's going towards this one, but it's not actually going to reach it because, of course, it's reaching the lens first, which is going to diffract it. So it's going to go as if it's going towards the focal point, and that is the light ray that's going to refract parallel to the principal axis. Okay. Of course, we already know that this is a diverging light ray, so let's dot back while we still have the ruler here. Okay, so next one, optical center. Thankfully, that one doesn't change at all. So that one's nice and easy. Going through the optical center, you can always count on that light ray to never change. That's just always going to go straight through. Okay. And then we have our final one. So that one's a little bit different. So it still starts going parallel. But again, we know it's not going to converge on the focal point on the other side. So it goes parallel. And then this is the one that diverges from the focal point. So what's going to happen is it's going to go off as if it's coming from this focal point over here. Okay, so that's how that one's working. Again, we better dot back because we already know that this is a diverging lens. All right, and where do our three lines meet up? They meet up right there. Okay, so what's this telling you? It's telling you that a diverging lens is always going to create a virtual image that is, that is upright, but of course we already know that. We already know that upright images are always virtual. Virtual images are always upright. But this is telling us that this is always going to make something smaller. Okay, so these lenses are used if you need to make a smaller image rather than a larger one. So if you need to take something really big and make it look smaller. Okay, so those are what's happening with our images. So again, image characteristics, we describe them the same as mirrors. The equations are the same for mirrors. The sign conventions are the same for mirrors. Yay. Okay. So let's just take all that information onto this one. But as far as images go, if the image shows up on the opposite side of the lens from the object, then it's a real image. And then if it's on the same side of that lens, it's going to be virtual. All right, so let's just summarize everything that we've learned about converging mirrors and lenses and diverging mirrors and lenses, okay? So what about DI, the distance of the image to the mirror or the lens? All right, well, with a converging mirror lens, we had 3 different possibilities. So what if the object was placed further away than F, the focal point? That got us a real image, okay? And therefore our image distance is positive. So when we have a real image, the distance of the image to the lens or the mirror is positive. There was another situation when the object was placed at the focal point. What happened there? There was no image. So not real or virtual, just no image. So nothing's going to happen there. And then there was a situation when the object was placed closer to the mirror or the lens than F. So it was placed in between F and the mirror or the lens. And that's when we got virtual images, which are, of course, negative for the distance of the image to the mirror or the lens. For diverging mirrors and lenses, it's so much easier, so much simpler. It was always a virtual image, right? So therefore the distance of the image to the mirror lens is just always negative for a diverging mirror lens. Okay, let's talk about the height of the image. So we had 2 situations here. Of course, we're not looking at the situation where the object is placed at the focal point. Okay, so for converging lenses here, when the object was placed further away than the focal point, we got an inverted image because, of course, it was real. And we know when we have a real image, it's always inverted. So that was a negative image height. And, of course, when our object is placed before in front of the focal point, then we got an upright image. And we know that, of course, because it's a virtual image, and our virtual images are always upright. So then, therefore, our height of the image is always positive. Again, with the diverging mirror lens, since it's always virtual, it's always upright. Okay, so then the height will always be positive. And finally, our focal point for a converging mirror lens is always real. So therefore, it always has a positive focal point. If you ever have a diverging mirror or a diverging lens, that is a virtual focal point. It's going to be negative. And it is so, so important that you get these positives and negatives in the right place. If you don't, yeah, it can be tough for you. Well, let's just do a few examples with the same equations that we used from yesterday. And I promise I'm done talking, and then we're done EMR, if you can believe it. Well, at least all the content. So there we go. We're almost done. So we have a glowing object. Ooh, that's 2.5 centimeters tall. So it just gave us the height of the object. It's placed 15 centimeters from a converging lens. So it just gave us the distance of the object to the lens. Converging lens, okay. If the lens has a focal length of 7.5 centimeters, so we know that's going to be positive because it's a converging lens. So there's the focal length. We want to determine the image distance, the image size, and the characteristics. So basically, what are we trying to figure out? We're trying to figure out, is it in front of the focal point or behind it, right? Because that's kind of going to tell us if it's virtual or real, right? Which tells us if it's upright or inverted. So looks like we can go ahead and start right by finding the image distance, okay, using this equation right here. And we solve for the image distance. So when we calculate that, we get an image distance of positive 15 centimeters. Interesting. What was the deal when DI was positive? Anybody? Let's go back and look. When DI is positive here, oh, it's real. It's a real image, so therefore it must be inverted. There we go. And then bigger or smaller, if you can remember that, then that's awesome. So we know that this is a real image. We've just figured that out. Okay? So this is a real image. Okay, let's figure out the image size. So we can use that using this magnification equation. Okay, so I'm looking for the height of the image. So it's just equal to negative di times HO over DO. Okay, so if we do that, we know that the image height is negative 2.5 centimeters. Okay, so that's what we expected, right? Because we knew that the image would be inverted because we know it's a real image. Also, so what do we know about its size? Well, the height of the object was, oh my goodness, 2.5 centimeters tall. And this is also 2.5 centimeters tall. So that actually just told us two things. So first, it told us that it's inverted because, of course, it's negative. And then it also told us that it's the same size as the one before it. Can you remember which situation that was? Let's go over. Looks like it's this one where it was at 2F. So there we go. So that's what's going on. Okay, so that's how you can use, you basically, again, you're using the exact same equations, but now for lenses instead of mirrors, okay? So really it's this. You just really gotta know this, okay? Know what a converging mirror and a converging lens is, okay? So remember, converging lens here is your convex lens, and your diverging lens is your concave, okay? And then know what your converging mirror is and your diverging mirror is, which is which is concave, which is the convex, which is converging, which is diverging. If you don't remember, I'm going to leave that for you to go look up, okay? Because if I just tell you, you're not going to remember. So you go look it up if you don't remember. That's it. We're done EMR. Yes. Okay. So good luck working on this stuff, and let me know if you have any questions.